Welcome everyone to this webinar by Babak Ebrahimi. The topic today is performance measures of road infrastructure, a life cycle thinking approach. This webinar is being recorded. Your name will not appear on the recording unless you speak out when we ask for questions. Please save up any questions that you have for the end, and if you want, I can read up the question that you have. Then just write it in the direct message, and your name will not appear in that case. Once again, this is one of the in the series of free webinars that we have in the Coastal Highway E39 project. So thank you all for listening in. Okay, Babak, please.
Yeah, thank you. Before I start, I would just like to thank Norwegian Public Road Administration for financing this PhD, and also which was through this program, Coastal Highway Route E39. And also I would like to thank my supervisors and colleagues who've been helping me take this journey in a very smooth and nice experience. The outline of today's presentation is going to be something like this. I'll start by giving a bit of a background about the importance of road infrastructures and also the role of infrastructure in Norway. After that, I'll explain the aim of the research that I carried out and what research questions I formulated to reach the main goal. And after that, I explain what research approaches I introduced for each research questions and what were the main findings. Next, I conclude and show the future research potentials, and at the end I'll show the limitations that this research had. Well, it is hard to imagine a day with no road. As a matter of fact, they are so important for us that their inexistence would paralyze the existing of our yeah, there's a bit of a glitch in the slide. I don't know, because the thing doesn't show up the way that I was hoping for. Yeah.
Yeah, now I think it's showing.
Okay. Yeah.
But just go back to slide number 2 and yeah.
Yeah. Yeah, because the problem is it doesn't follow the same graphs that I was hoping for also. It's a bit weird. Anyhow, hope it's gonna be okay. So it's hard to imagine that a day with no road infrastructures. They are so important for us that their inexistence would paralyze the existence of our society and civilizations. Therefore, high amount of investment every year is allocated to sustain the existing infrastructure to assure that we get the service we need. And beyond that, fresh investment every year is allocated to upgrade the system and create added value to the existing infrastructure that we have. However, due to constant need for construction and maintenance activities, high amount of natural resources is extracted from our finite planet, and down the road more materials become scarce. And due to these constant maintenance activities, more waste is generated that pressure our ecosystem. Therefore, it is very important to take a systematic approach, aka life cycle thinking to assure that we tackle all these aspects and assure that we are avoiding partial thinking and problem shifting later on. Oh, this. Oh, it goes. It doesn't. I'm very sorry. The slide doesn't follow because. Shall I share my screen instead, if it's possible?
Yeah. Yes, I think that's best.
I will share my screen. Do you all have it?
Yes, you can see it clearly now.
Okay, perfect. Norway is a country of about 5.3 million people, and the majority of the population is located around the coastal area. And road infrastructure plays a fundamental role for Norwegians to get closer together and help, and having a secure and effective road infrastructure support the socio-economic activities in Norway. As a matter of fact, about 88% of the transportation in Norway happens on road. And over the last years, the road network has expanded continuously. And at the moment, we have about the total length of 93,000 kilometers of public-owned road. And due to the importance of road infrastructure, Norwegian government also aims to spend a staggering amount of Norwegian kroner over the period of time to assure that they increase the safety, efficiency, and effectivity of the transport while modernizing the infrastructures. They focusing on different areas, but regarding the environmental concern, the government likes to cut the carbon emissions by half by the end of 2030, by the year 2030, and this should be achieved from both construction and maintenance works. And beyond that, due to the constant expansion of the network and increasing the technical requirements, road infrastructure hasn't been maintained as they should have been. And because of that one, the maintenance delay in the network has increased, and this is one of the aims that the government hopes to achieve in the coming years, that they can close the gaps and reduce the maintenance backlog or maintenance delay in the network. The aim of this research was to explore and gain a deeper understanding of the life cycle of road infrastructure, and at the same time apply a systematic approach and propose solutions that close the research gaps. And this has been done by using Norwegian road network as a case, while I try to keep the results as generic as possible that can be used for other cases. In order to reach the aim of the study, I carried out literature studies to see what are the missing points. And in doing so, I was using research that they were in the domain of environmental and economic assessment of road infrastructures. And I tried to find those areas that they have high potentials and also create added values for the future research. Looking at the environmental impact assessment of road infrastructure, we can see that LCA has been used for many years, and it's been almost 2 decades that it's been used, and the studies use different kinds of approach to showcase the results. And over the time, we can see the resolution of the LCA because of increase in the better representative data. We can see the resolution of the LCA of road infrastructure has increased significantly. However, the prior study has a tendency to use generic data that they were showing the average industry average data on a global scale while showing the impact assessment for a particular case that they were studying, meaning that they were using global data to show a local problem. And at the same time, these studies show their impact assessment based on a single value without showing the uncertainties that their studies might have. Therefore, it became a research question for this PhD to understand how we can regionalize. How can a regionalized life cycle assessment be conducted while we're using generic life cycle inventory, and at the same time, while we're showing uncertainties of our assessment. The second research question that I formulated was about the life cycle, lifetime estimations. It is very important to have a very good idea about the longevity of materials. Whether we are doing life cycle costing, life cycle assessment, social life cycle assessment, or if it's about asset management, we need to know, we need to have a good idea how long the material lasts in our system. And having a good idea gives us having a increase the robustness of our study, reduces the biases, and at the same time it helps us to make informed decisions. However, when I was reviewing this environmental and economic study, I saw that there is a tendency to use average absolute lifetimes. By absolute, I mean single lifetimes, meaning that material X only lasts for X amount of years, and material Y lasts for another time frame. But all of them are shown by a single value. And the problem is, when we are using absolute lifetime, we have a tendency to not show what would be the uncertainties of us, how accurate and reliable our lifetime value is, and at the same time, how much we can show the effect of different factors that they change the longevity of materials. Therefore, it became the research question of mine to introduce an approach that we can show the estimation of lifetime based on the effect of different variables, or others say, how can a multivariate lifetime estimations can be conducted. And another research questions that are formulated was relating to physical accounting of road infrastructure. As a matter of fact, we have continuously put many materials, different form and technical mechanical properties of material in our infrastructure, but we have not a very good idea about how much we have in a system. This physical accounting has become more a hot topic these days because we are living in a finite planet, and creating a more circularity of our resources has become a solution to bypass the limitations that we are facing. And because of lack of physical accounting, it become another research question of mine to find how we can show how much road infrastructure do exist in Norway. Therefore, my research question was, how can the long-term physical accounting of road networks at the national level be modeled? Based on what information we have and what kinds of models we can use to show such an accounting on the national level. And to scope the research, I focus on certain areas for the life cycle assessment. When I wanted to show how we can use create a regionalized life cycle assessment among different product systems, I focus on construction material, meaning that I picked construction materials. There were various reasons that I picked construction materials as a product system to show how the regionalized impact assessment can be, regional life cycle assessment can be done, and how we can do the uncertainties. Because construction material, if you look at the literatures, they are responsible for about 15 to 30% of the climate impact. And at the same time, these impacts directly related to operation during the earthworks, if it's a cotton field and the transportation of materials, and also they are directly are contributing in the embodied impacts when we are quarrying materials. If we are thinking of minerals that are going to be used for the construction for the construction of road infrastructure, for building in road infrastructure, we can see that construction machinery take about 50% of the impacts embodied in the producing minerals like aggregates or other kinds of materials that we can think of. Therefore, it became very interesting for me to look at construction machinery as a product system while I'm answering the research questions. And more than that, construction machinery hasn't been studied in the prior LCA studies. And there were few, but they are very outdated. And because of that one, I was really interested to look at construction machinery. And related to the lifetime estimations, we decided to focus on the pavement materials because there is a gap in knowledge, and we wanted to get there are expert knowledge that they know how much material lasts, but we wanted to use a numerical model to show how we can actually estimate and how close our estimation is with the experts' knowledge. And regarding the physical accounting, which was about how much material we have in the network, I looked at the whole the value chain from construction material usage and end of life that it comes to maintenance activities. So we focus on that domain, but while we're looking at the entire road networks in Norway. To answer the first research questions, how can a regional life cycle assessment be conducted while using generic life cycle inventory? We were fortunate to have access to a very nice data that has been compiled by the Norwegian Association of Heavy Equipment that show how the construction machineries has been operated in Norway. And there were many machinery, but we focus on 5 categories of road construction machinery, and in total we looked at 14 units. And these construction machinery machines were articulated hauler, motor grader, wheel excavator, wheel loader, and crawler excavator. So these were the 5 categories that we looked at. And when we were thinking of performing a life cycle assessment, the system boundary that we decided our system boundary was from extraction of raw material to pre-manufacture and transport the material to factory to assemble construction machinery until the time that they are decommissioned and they need to be disassembled and do the waste management at the end of the life cycle. Meaning that we carried out the full life cycle approach from the cradle to grave of each construction machinery. And the functional unit that we used was one construction machinery over its economic lifetime. And and this functional unit was used to show what is the total impacts of the construction machinery for each construction machinery. And carrying out when we build the inventory and we use EcoInvent database, and we regionalize that database, and also we use some additional information from the producers and from some EPD, environmental product declaration reports, to create a more tangible inventory data. When we had that one, we run the model in SimoPro software, and we use CML impact assessment method. Among 11 impact assessment impact categories, here I just show 3 of them, which are abiotic depletion, global warming, and freshwater ecotoxicity. And on a x-axis, we can see the relative impacts associated with each impact categories, with each construction machinery, and the y-axis shows which construction machinery we are talking about. Is it a wheel loader? And the 32 is the operation weight of each machinery. It's a wheel loader 32 tons, or if it's a crawl excavator 16, which is 16 ton operation weight. And yeah, and we show and these bar charts are normalized, so meaning that we relatively compare these impacts associated with each construction machinery. By going into the results, we saw that if the weight of machinery has an impact on the total impacts that comes from a machinery. In other words, if we have a higher operation weight, we have higher environmental impacts. And you can see that if we have an excavator which is 48 tons, it has in fact higher impact compared to the lower operating weight construction machinery. And the reason for that was related to having the higher mass of materials that were used. And also beyond that, it was due to the higher engine capacity that this construction machinery had. Which brings us to the next point. The operation phase showed that was in fact the dominant factor for among all impact categories that we were focusing on, meaning that the amount of fuel that was used and the tailpipe emissions in total results were the dominant phases of a construction machinery that were causing the high impact over the full life cycle of each construction machinery. However, base material were the second most important contributor, and that was due to the assembly of the materials and also the sequential repair and services that we needed to have, like changing parts, changing filters, oil, and etc., etc. However, in this study, we also found that end of life phase that was often discussed as the least important phase of a construction machinery or any kind of a product, because there is not much is going on there. We found that depending on the scenario that we use, how waste material needs to be treated, the end of life phase might have a contribution. Here we can see that the freshwater ecotoxicity, because of the scenario that we use, we can see that there is a contribution from end of life of material. And as a matter of fact, in the assessment, we consider at the end of each tire, when we have the tire that they are worn out, this tire is used as an energy source for operation of for producing cement. And because of that kind of a scenario that we consider, we can see that end of life phase is not insignificant with respect to the impact, and has a has a contribution over the full life cycle of machinery. And more than that, we were thinking of carrying out an uncertainty analysis to show the accuracy and reliability of our assessment. In doing so, we did the Monte Carlo simulations for all of these machines, and we carried out and we iterated for over 1,000 times of iterations. And here we show the results, the same table but with another angle. Here we show the total impact with respect to each construction machinery, and we use box plots and kernel distribution plots to show the intensity, the probability, and of the impacts. And if we look at the mean value of these impacts, which is the middle of the box plot, we can still get to the same conclusion that the heavier machine is, the higher impact it has. However, if we look at the upper and lower bound of each distribution, we cannot say with 100% certainty that always the heavier machinery, the heavier a machine is, it has the higher impact it has. Meaning that there might be with some percentage of certainties, we can say that a particular machine is often having a higher impact. And this brought me to the point that performing uncertainty analysis gives us an opportunity to look at the picture from another angle and say how certain are we with this kind of single values that we are providing in the impact assessment. To summarize our findings, I can say that the dominant contributor in this study was operation phase and base materials among all impact categories, and also it was a very important of the findings that showed that carrying out a full life cycle assessment provides us an idea of a better picture, and with respect to the scenario that we pick, we can say that inclusion of end of life phase actually matters, because it gives us a better picture that how our waste treatment might actually impact the whole lifetime of if you look at the product from a full life cycle perspective. And also, we found that it is necessary to perform the uncertainty analysis to get a better picture from the reliability and accuracy of our decisions when we are taking what would be the impacts associated with the product. Regarding the second research questions, that was how can a multivariate life cycle estimation be conducted? Well, we focused primarily on pavement materials, or more specifically only asphalt bituminous material. We focus on only the estimation of these kinds of material. And the approach we took was collecting. First, we needed to do the data engineering of the data, because we used the data from the Norwegian road depository, the road data bank depository, and we used these data to prepare the data to do the post-processing for the statistical assessment. What we did, I did the fetching, cleaning, and merging different data sets from this depository that I had the access to. And also, I use a spatiotemporal analysis to overcome some of the limitations that they were embedded in the database, to join the data and create and harmonize these data that I had the access to. And also, I use monitoring of the maintenance works there were some some issues with the database, because not all the maintenance activities has been registered in the Norwegian road database. So in order to monitor how the maintenance activities has been done over the last couple of years, I use a specific measure to cross-validate the recorded maintenance activities, and the variable that I use for measuring the cross-validating the recorded maintenance was one pavement distress that has been measured by the Norwegian Public Road Administration, which was Rutting. And if you do not know what Rutting is, if you look at the road, rutting happens. It's a distress that creates a deformation on a pavement with such a profile, and happens across the wheel path of a road. And you can see it in some of the roads, that some of them are very severe and some of them are really not so severe. And that was a response variable. This rutting was a response variable that we used to cross-validate the recorded maintenance activities. And for the statistical model, I use survival analysis to do the estimation of the lifetime. And among different survival models, I use Cox proportional hazard model to do the semi-parametric analysis of data. And various inputs were considered. This was a regression and a model, so I used different variables to check what is the effect of different factors on the lifetime of each pavement. And these were the variables that I considered, and for each, and also I stratified my assessment, meaning that I grouped each assessment based on the pavement types, meaning that I compared each pavement performance relative to each other. And the data that I collected were coming from these three counties from Norway. So I considered Troms, Sør-Trøndelag, and Vest-Agder as the three counties, and I picked these counties because of the considerable climate difference. If you look at the average temperature, outdoor temperature for these three counties, you can see that over the last 10 years, the average outdoor temperature is like this. So they have almost 2.5 degrees temperature difference. And also, there were different road networks in a system. So the red paved line, or the paved lines, are the road that I consider for the estimation of lifetime. And these roads were chosen. I chose a road that they had the annual average daily traffic between these ranges. And I chose these roads because Rutting was shown to be a very good Rutting is a pavement distress that happens in roads that are in this range of a traffic volume. And more than that, I classified the roads with respect to these classes. And these are the classes that has been introduced by the Norwegian Public Road Administration. So what the actual results show when I look at it. First things I wanted to do was doing the non-parametric analysis. I wanted to show how the maintenance activities has been done, and meaning that what was the maintenance records. And also I wanted to look, if we consider the technical requirements that has been set by the road directory, how shorter the maintenance activity should have been, meaning that what is the gap between technical requirement and maintenance records. If we look at the mean survival probability and looking at the difference, we can see that the maintenance activities has been delayed for almost 2 years for each traffic class, relatively. And if we can also see that one when we look at the Norwegian policy, Norwegian National Transport Plan, that they are talking about the delay in maintenance activities. And here we can also see that if we follow the technical requirement, we should have maintained at least 2 years earlier than what we have done. And also another findings, because I did the Cox proportional hazard function, I wanted to see the effect of different variables. And these variables that I found that they were constantly significant across all traffic classes were aggregate nominal maximal size and heavy traffic volume, meaning that they showed in all these classes, these two variables had the constant low p-value. And however, I saw some uncanny results in the data. Sometimes, if you remember, one variable that I considered was a speed limit. Sometimes in one traffic class, increasing the speed limit resulted in a shorter lifetime of a pavement, but often also happened, and sometimes it was really unproportional. Sometimes increasing the speed limit was decreasing, and all of a sudden, so the profile of the increase or decrease in the speed limit did not match the expectations. So therefore, we use another explanatory variable to see what is the reason for it. And after discussion that I had with the road director, it became that it might be the reason due to the travel road width. And therefore, I considered that this variable to go dive deeper into this data. And surprisingly, we could see the effect of road width on rutting, meaning that when we had the narrower road, we could see that the rut profile the depth of a rut profile gets deeper and narrower. And when we have a wider road, the profile gets more relaxed, the depth is shallower, and the spread and the width of a rut is also wider. And to summarize the findings, we were able to show the gaps between the maintenance practice and technical requirement. Based on the model and the data cleaning and the stuff, we could show what is the gap actually between the maintenance practice and technical requirement. And also we were able to see the effect of different variables on the longevity of pavement materials, and to get a better understanding about the lifetime of the materials. And when we are using these values for later on for any kinds of assessment and having a better robust decision making. Going to the third research questions was, how can the long-term physical accounting of the road network at the national level be modeled? So in doing so, we decided to carry out the dynamic material flow accounting. Flow accounting in the sense that we wanted to follow how much material goes into the system, goes out to the system, and how much stock we have. A stock here is the position of material over time, the position of material. And by the dynamic here, we are meaning the relative change or changes in the amount of stock, meaning that how much is being added or left from a system throughout the time. And to do that one, I use a bottom-up approach, meaning that I collected information from all the road networks in Norway and aggregate all the information to show how the stock is on the network. However, there are many roads. Here I just focus on 3 categories of road that the Norwegian Public Road Administration is responsible for. One is European road, national road, and county level road. So in total, about 55,000 kilometers of road that was studied in this research. And more than that, I focus on the retrospective and prospective. Retrospective in the sense that how maintenance activities or how the road network has been grown over the period of time until the present, and how the prospective, meaning that how the network might, or how the material consumption might be in the future. So retrospective looked into the past and prospective looked into the future. And the period of assessment that I considered was from 1980 till 2050, and the time that I had the data till was up to 2017, meaning that for the retrospective I consider only 37 years, and for the prospective was 32 years of analysis. And also I consider uncertainties to show what is to avoid providing in single values. So I wanted to create the more kinds of uncertainty analysis of data to show what will be the reliability and accuracy of the data. So like the previous research questions in lifetime estimation, I needed to collect the data and do the data engineering. So here was massive data engineering, doing a special temporal analysis to prepare data for post-processing. And in the post-processing, I used different kinds of model. And one of them was classified and regression decision tree model to do the prediction of what would be the layer composition of each road section. And because of that one, I use this decision tree model to train the data and then predict for the other sections that we didn't have information for, with respect to different variables that I consider. Other than that, I consider fitted survival analysis based on the knowledge that I attained from the previous research questions, lifecycle estimation, with respect to various variables. I was able to carry out a survival analysis and fit a distribution model to see how the probability of what is the probability of material with respect to their longevity. And more than that, we use empirical pavement wear, meaning that what is the effect of tire pavement interactions and how long pavements would last in our system, how pavements are dissipated from our system. And beyond that, I consider different scenarios: 1%, 0%, 1%, and 2% annual increase for the traffic volume for each sections, meaning that how the effect of increase in each section with different scenarios would increase on the maintenance requirements. And I should say that for the prospective, I did not include the effect of expansion of a network because I did not have any information about it. But the prospective here only focused on the preservation of the network, meaning that we consider periodic maintenance activities that requires to be done on each pavement section. And more than that, in the results that I'm going to show is going to be the 2% annual increase, the scenario that then I show the results to you here. So the retrospective, like I said, was between 1980s and 2017. And this is how the results, how the result shows. Here, the blue bar chart is how much material was inputted to the system. The yellow bar chart means how much material left the system, and red line is how much the network expanded with respect to the material. And if we look at the difference between 1980s and 2017, we can see that the network, or the amount of stock in the network, increased by 8 megatons. And the reason for that one was due to the maintenance work, meaning that maintenance work was responsible for 3/4 of the total growth in the stock, and the rest, 1/4, was due to the expansion of a network during the same time period. And when we look at the prospective results, that was from 2018 till 2050, we can see that over the same relative time, I mean, over 32 years, it is expected that the amount of stock would increase by 50 megatons. And as I said here, maintenance works and payment were the only sets of variables that they were discussed in this analysis, meaning that we did not consider the effect of network expansion and rebuilding and reconstructing, building new roads in the system. And to summarize the findings, I could say that the material stocks of road infrastructure would continue to grow, like what we saw, and the maintenance work showed to be the main contributors. Both, when we look at the based on the retrospective results, we could see that the 3/4 of the impact was coming from maintenance activities. And because of maintenance activities, because of the current condition of infrastructures and the importance of road infrastructure, we could say that the maintenance activity would still play a fundamental role in the consumption of raw materials, like minerals that we're going to use, or any kinds of bitumens. And more than that, we saw that the demand for more road materials would increase. Meaning that due to the constant growth in the maintenance activities, and if we probably have road expansion, we definitely need more material for expansion of the system. To conclude the whole results and the findings from these 3 research questions, I can say that this research recommended approaches based on the gaps that we found within these scientific literatures, and also the potentials that was we found with respect to the national road infrastructure policy through the National Transport Plan. And for that, we focus on the life cycle assessment of construction machinery to show how we can create a regionalized study while showing uncertainties, and also focus on construction machinery because of their key element that we can actually use to use it as a baseline when we are using other scenarios in order to achieve these 50% cutting climate impacts from construction activities, construction or maintenance activities. And more than that, we use the estimation of payment lifetimes to first show how it's possible to estimate the lifetime of materials, and second of all, to improve the robustness of the analysis and improve the decision making. And also, we use this modeling of the long-term physical accounting to get an idea how much material actually exists in the system. And if we're gonna do urban mining in the future, we get some sort of idea how much material do we have in network, and maybe we can reuse or recycle these or repurpose this material for other kinds of construction activities later on. This study wasn't without any limitations. I should say that here I only focus on open road infrastructure to answer these research questions, and also I focus on the current state of road infrastructure. So I didn't focus on or consider any modern cutting-edge technologies that are still on a laboratory base. So what I considered was what is the current practice in road infrastructure, construction and maintenance activities. And also I use different methods and models. However, there are many more that can be used that can be considered. However, these models and method that I chose was based on the literature and their significance and the potentials that I observed through the literatures. And also there was some lack of information that stopped me to do more. So because of that one, I wasn't able to do everything. Like if you think of this construction, this stock modeling of the road infrastructure, I couldn't do for the entire road networks because the data weren't there, or we didn't have enough information to carry out. But about the future research, I should say that life cycle assessment has been done for a while, and it becomes more prominent in the future. However, the current LCA study is incapable to consider risk assessment into it, or integrate risk assessment. And this is due to the inability of LCA to capture the availability of abiotic resources from the site of the production. Meaning that if the current LCA study can show the consumed mass, energy, and geological depletion, but they are incapable to show the supply side risks, meaning in order to answer these limitations in the current LCA study, it might be beneficial to consider the economic scarcity potential or geographical supply risks to create a more or increase the reliability of the LCA study that we are carrying out. More than that, it's going to be very important to consider performing optimization studies to answer these multi-objective issues that we always have. We want to reduce the cost while we have the reduce the maintenance, while improving the quality of the network, while we're doing so and so. It's really important to carry out these kinds of mathematical models to get the most optimum for the money spent. And also this study by itself focus on a very small area. It is beneficial to couple the research finding from this research with the other research studies that are currently ongoing, and some of them are done, to help Norwegian Public Road Administration to get a more comprehensive approach, because one PhD by itself is not enough. However, there has been many PhDs or researchers or postdocs or so on and R&D results that they are there. It is very important to compile this and put all these findings and disciplines that has been multidisciplinary results into one package to assure that information is not going to be lost. And by that, I would say thank you very much for your attention, and I'm looking forward to hear your any questions that you have.
Thank you so much for a really nice presentation, Babak.
Thank you.
I think we'll, as you say, just open up for questions.
Mm-hmm.
You can probably just share your presentation.
Oh yeah, absolutely.
Continue to share your presentation.
Yeah, absolutely.
Don't hear anyone speaking out. So I think I'll just once again say that thank you so much for a wonderful presentation.
Thanks.
What is next in line for you now?
At the moment, I'm trying to answer some of these because I sent the papers to journals. I'm trying to clean up those things because I need to get back to, correct some of the uh, parts that hasn't been properly described or need more kinds of explanation. So I'm just answering some of those works that is going on in these research papers that I've done, and also try to work uh, on a case that I've been happy to get from Trondheim to just further expand my findings and show that how the maintenance activities can be done from a more of a network perspective, and that's I'm hoping for to achieve in a short time, to actually show the potential of my results and findings in a sort of a small deliverable.
Well, it sounds very interesting, and I wish you good luck with that, and I look forward to seeing the results from that as well.
Yeah, thanks.
So unless anyone have any more questions, I think we'll just say once more, thank you so much for your presentation.
No, thank you very much.
And thank you all for joining in and listening into this webinar. It will be made available on our webpage later on.
Yeah.
Thank you so much.
Thanks. Thank you very
Bye
much.
bye.
Bye.